In this video, we're going to start Experience 11, in which we are going to look at the details of a hypothesis test. In Experience 10, we went through the overall structure of a hypothesis test, but we did not focus on any of the calculations. And that was to serve as developing the foundations for these hypothesis tests without getting too bogged down with the numbers. So we're going to go through that whole process now, and now is the time that we're going to do the calculations. The essence of a hypothesis test, we are going to focus on the population proportion. This could be applied to a population mean, but we're just going to focus on the proportion. And the essence here is that we want to see if a sample proportion is consistent with a population proportion. Let's run through this procedure, and some of this will serve as a review as well. So the first step is to define the null and alternative hypothesis. This is usually represented with HO and H1. Sometimes it's HA, so just be prepared to see both versions there. And that is where you say, like, the population proportion equals the null hypothesis has the pre-established or baseline number. And you usually write a number there, but I'm actually going to write P0. And that's just going to be representing the baseline number. The alternative hypothesis has that same value written, but remember, this can be a two-tailed test, a left-tailed test, or a right-tailed test. So it's not all three of them. You pick one of those. The next step is computing the test statistic. So that is a new step for us. Right now, I think I'm just going to run through the procedure and not get bogged down by that formula, so I'll come back to that. The third step is determining the p-value. These are our quantitative-based steps, and we're going to give them their own time in just a minute. Our last step is to state a conclusion. That conclusion is either we reject the null hypothesis or we do not reject the null hypothesis. So those are our steps, and we've, in the previous experience, got practice with defining these hypotheses based on a description of a problem and what the conclusion could imply about that pre-established proportion. So we've skipped these calculation-based steps, and that's what we're going to focus on today, is what do we do in those steps. Let's start with the test statistic. This is essentially like a z-score. It tells you how far away these two quantities are in terms of standard deviations. So you've got your sample proportion, and it's going to be different, most likely, from the hypothesized proportion. That's from the null hypothesis, the pre-established value. But how different are they? And so that's quantified in terms of standard deviations. So I'm going to write a formula here, and this formula will hopefully look a little similar because we've seen it already. We've been building up to this stage for the past several weeks. This starts with p hat, the sample proportion. And we want to see how far away it is from the proportion in the null hypothesis. How different are they? Divide by the standard deviation for the proportions. We saw this was p times 1 minus p over n. But the tweak that we will put here is that this P needs to be that number from the null hypothesis. So go ahead and put that in a box. We're going to use that quite a bit. That is our test statistic. Let's talk about potential values for this test statistic. It's just a number. But when we perform this computation, this is an indication of how different our sample is from our hypothesized value in terms of proportions. So if you get a test statistic and it is a large number, I'm going to put that in quotes, that must mean that your sample proportion was very different from the number in the null hypothesis. That would probably correspond to having evidence for your alternative hypothesis, that you would reject the null hypothesis. On the flip side, what if you have a test statistic that is not large, maybe near zero? There is probably not evidence for the alternative hypothesis, right? Because the alternative always says something to the extent of, these things are different, this thing is bigger. But if you get a number near zero, zero is indicative of not significantly different. Therefore, this conclusion would be, do not reject the null hypothesis. Sometimes we say we fail to reject the null hypothesis. Same thing, do not reject, fail to reject. I was being intentionally vague here when I said, suppose the test statistic is large or near zero, because we need to draw a line, some sort of threshold that differentiates something that is large from something that is not large. And that is accomplished with this next step, the p-value. Let's discuss this thing called a p-value, which is short for probability value. From a procedural perspective, the p-value is the area in the z-distribution beyond the test statistic in the same direction that is stated in the alternative hypothesis. So it's an area. We know how to find area in the z-distribution, right? Because we know how to use the z-table. From a hypothesis testing perspective, this is a probability of observing results that you saw from your sample statistics, at least as extreme as the ones that you observed. And this is assuming that the null hypothesis is true. So this is a technical definition here, but it is just a probability. It is just an area. Let's consider what the connection is here between a test statistic and a p-value. If a test statistic is large, then in the z-distribution, zero's in the middle, the test statistic, it could be positive, it could be negative, it might be way over here. It could be way over here. I'm going to put a negative sign in it for clarity. The corresponding p-value would be the area beyond. Now, if it was right-tailed, it would only be this right-tailed area. If it was a left-tailed test, it would be just this left-tailed area. If it was two-tailed, it would be both of them. A test statistic that is large is going to get you a p-value that is small. Let's consider the contrast here. What if you had a test statistic that was small, maybe somewhere near 0? Again, it could be positive, it could be negative. I'm doing both for the fun of it. If we had a test statistic near 0, the corresponding p-value would be quite large, yeah? It would be this whole shaded region. If it was right-tailed, just the right region. If it was left-tailed, just the left region. Two-tailed, both of them added up. So a test statistic near 0 is going to result in a p-value that is large. And again, I'm being vague. What is large? What is small? Because that's how we're going to base our conclusion. We said already a large test statistic is indicative of a difference. That would result in a small p-value. That would result in a rejection of the null hypothesis. On the flip side, a large p-value would be do not reject the null hypothesis. Again, what is big? What is small? We are going to use our p-value to determine our conclusion regarding the null hypothesis. When we reject the null hypothesis, that is because the p-value is small. Our threshold for small is less than alpha. On the flip side, we do not reject the null hypothesis when the p-value is at least alpha. Remember what alpha is. Alpha is usually a small number, usually 0.01, 0.05, or 0.10. Those are the most common ones. So we say if we get a test statistic that is so large that it results in a small p-value, that gives us evidence that the population proportion probably is not what you once thought it was, because the chance of it happening was so small. On the flip side, if you get a test statistic near 0, that means your sample was fairly consistent with whatever is stated in the null hypothesis, and that we should not reject whatever is in the null hypothesis as being legitimate. So here in this video, we've got the formulas laid out. We've got our conclusion, which is based on that p-value. And in the next video, we are going to look at a particular example from head to toe and crunch some numbers.